Imagine a cosmic classroom where physics meets imagination. You're watching a mesmerizing demonstration that will transform how you perceive the universe. Picture a taut, elastic fabric stretched out before you, a simple representation of the vast cosmic canvas we call spacetime. Now place a heavy ball right at the center. Watch carefully as the fabric begins to curve and sink, creating a gentle depression around the ball. As you release a small marble nearby, something extraordinary happens. Instead of rolling in a straight line, the marble's path begins to bend, following the curvature created by the heavier object. This isn't magic. This is the essence of Einstein's groundbreaking general theory of relativity. In this single elegant moment, you're witnessing how massive objects fundamentally reshape the fabric of reality around them. This seemingly simple experiment captures the revolutionary heart of Einstein's insight. Gravity isn't a mysterious pulling force, but a fundamental warping of space and time itself. The marble doesn't get pulled towards the heavy ball. It's simply following the most natural path through a curved space-time landscape. Such a profound concept would completely reshape our understanding of the cosmos, transforming physics from a mechanical science to a dynamic, interconnected view of universal geometry. Our cosmic journey today will unravel the most mind-bending implications of this theory. We'll explore how gravity emerges not as a force, but as a consequence of curved space. We'll discover why time itself flows differently depending on your position in the universe. We'll demystify black holes, revealing them not as cosmic vacuum cleaners, but as extraordinary regions where space-time behaves in ways that challenge our everyday perception. And here's the truly fascinating part. This isn't just abstract scientific theory. General relativity isn't confined to textbooks or distant astronomical observations. It's a living, breathing framework that impacts your life right now. Your GPS, those navigation systems we rely on every day, would be completely inaccurate without accounting for the time dilation predicted by Einstein's equations. Before we bend space and time together, I invite you to join our cosmic community. Just like gravity shapes the universe, your engagement shapes the future of scientific exploration. Subscribe to our channel and become part of a journey that continues to unravel the mysteries of our incredible universe. Get ready to have your understanding of reality transformed, one cosmic revelation at a time. In the quiet solitude of the Bern Patent Office in 1907, Albert Einstein experienced a moment of profound revelation that would fundamentally transform our understanding of the universe. Working as a patent clerk, far from the traditional academic corridors of scientific research, Einstein's mind was continuously wrestling with the deepest mysteries of physical reality. The breakthrough came as a simple yet profound thought experiment. Imagine a person in free fall, perhaps dropping from a great height or floating in an elevator disconnected from external gravitational influences. In that moment of perfect, unresisted descent, something extraordinary happens. The person would experience no sensation of weight. They would feel completely weightless, as if gravity momentarily ceased to exist. This seemingly mundane observation concealed a revolutionary insight. Einstein realized that the experience of gravity is fundamentally relative. What we perceive as the force of gravity could actually be reinterpreted as the natural consequence of objects moving through curved space-time. The falling person isn't being pulled down. They're simply following the most natural path through a geometrically warped cosmic landscape. This epiphany, which Einstein would later describe as the happiest thought of my life, became the conceptual seed for his general theory of relativity. It challenged centuries of Newtonian physics, which had viewed gravity as a straightforward attractive force between masses. Instead, Einstein proposed a radical reimagining, gravity as the curvature of space-time itself. The implications were staggering. Massive objects like planets and stars don't just exist in space, They actively reshape the fabric of space and time around them, like a heavy ball creating a depression on a stretched rubber sheet. Celestial bodies create geometric distortions that guide the movement of other objects. This insight would take Einstein 8 more years of intense mathematical and philosophical exploration to fully develop into the general theory of relativity, published in 1915. But that moment in 1907, in a humble patent office, represented the conceptual breakthrough that would revolutionize our understanding of the cosmos. Einstein's thought emerged from a profound ability to see the extraordinary within the ordinary, to look beyond conventional understanding and imagine reality from an entirely new perspective. It was a testament to the power of human imagination and scientific creativity, demonstrating how a single, elegant insight can fundamentally reshape our comprehension of the universe. Imagine the universe as an intricate, dynamic fabric that weaves space and time into a single, interconnected medium. This concept of space-time represents a radical departure from traditional understanding, transforming how we perceive the fundamental structure of reality. Every object with mass, from the tiniest grain of sand to the most massive galaxy, creates a unique geometric distortion in this cosmic fabric. Picture a stretched trampoline surface where each object acts like a weight, creating a localized depression. Larger masses create deeper, more profound curvatures, while smaller objects create more subtle warping. But here's the revolutionary insight. Objects don't actually attract each other through some mysterious force. Instead, they're simply following the most natural paths through these curved space-time landscapes. A planet orbiting a star isn't being pulled, but tracing the most efficient route through the star's space-time curvature. A light beam bending near a massive object isn't being deflected, but following the most direct path along the curved space-time geometry. When you gaze up at the night sky, you're witnessing this cosmic dance in real time. The seemingly complex motions of celestial bodies are actually elegant responses to the underlying geometric structure of space-time. Planets, stars, and galaxies are not isolated entities, but active participants in a dynamic, interconnected cosmic geometry. This perspective transforms gravity from a force into a fundamental property of geometric relationship. Mass tells space-time how to curve, and curved space-time tells matter how to move. It's a continuous, reciprocal conversation between matter and the fabric of reality itself. Einstein's insight reveals a universe far more interconnected and dynamic than previously imagined. Every object, regardless of its size, contributes to the cosmic tapestry, creating ripples and curves that guide the movement of everything around it. We're not just observers of this cosmic landscape, we're integral participants in its ongoing, ever-changing geometry. General relativity isn't confined to abstract theoretical physics. It's a critical framework that impacts our everyday technological world in profound and practical ways. Perhaps the most tangible example is the global positioning system, a technology millions rely on daily for navigation. GPS satellites orbit approximately 2,200 kilometers above Earth's surface, where gravitational effects and motion create fascinating time-related phenomena predicted by Einstein's theory. At this altitude, these satellites experience time differently compared to receivers on Earth's surface. Specifically, time moves slightly faster for satellites than for ground-based systems, a phenomenon known as time dilation. Two key relativistic effects come into play. Satellites experience weaker gravitational pull, causing time to pass marginally faster. The high orbital velocity of satellites also impacts temporal progression. Without accounting for these time differences, which amount to approximately 38 microseconds per day, GPS navigation would quickly become catastrophically inaccurate. A miscalculation of just 10 microseconds could result in positioning errors of nearly 3 kilometers. This means your navigation system would potentially misguide you by several city blocks with each calculation. Engineers and scientists must continuously calibrate GPS systems, applying precise relativistic corrections to ensure accuracy. This real-world application demonstrates how Einstein's seemingly abstract theory of spacetime curvature directly enables critical modern technologies. Beyond GPS, general relativity influences numerous technological and scientific domains. Atomic clock synchronization, astronomical observations, satellite communication systems, gravitational wave detection. The theory reveals a universe far more dynamic and interconnected than classical physics suggested, where time and space are not static backdrops, but active, malleable components of reality itself. Imagine a universe far more extraordinary than our everyday perception suggests. A cosmic landscape where reality itself becomes fluid and malleable. General relativity unveils phenomena that challenge the very foundations of our understanding, revealing a reality more bizarre and interconnected than we could have ever imagined. Black holes represent perhaps the most mind-warping manifestation of Einstein's theory. These cosmic enigmas are regions where space-time becomes so profoundly curved that the traditional roles of space and time dramatically transform. At the event horizon, the boundary of a black hole, our familiar concepts of linear time and three-dimensional space completely break down. Gravity becomes so intense that time itself appears to slow down and space begins to fold, creating a realm where conventional physics loses all meaning. Gravitational waves offer another extraordinary glimpse into the fabric of reality. These are literal ripples in space-time, cosmic reverberations that travel across the universe at the speed of light. Imagine massive celestial events like colliding black holes or exploding stars, creating immense distortions that propagate through the cosmic fabric, stretching and compressing space itself. These waves were purely theoretical until 2015, when scientists finally detected them, confirming one of Einstein's most radical predictions. The bending of starlight represents another stunning validation of general relativity. Massive objects like galaxies and galaxy clusters can actually warp the path of light, creating spectacular gravitational lensing effects. A distant star's light can be bent around a massive object, creating multiple images or magnified views, essentially transforming massive celestial bodies into cosmic magnifying glasses. This phenomenon allows astronomers to observe objects that would otherwise be invisible, revealing hidden corners of our universe. The expansion of the universe itself emerges as perhaps the most profound implication of Einstein's theory. Space is not a static container, but a dynamic, stretching medium. Galaxies are not simply moving away from each other, but are being carried along by the expansion of space-time itself. This means the universe is continuously growing, with distant galaxies receding from us at ever-increasing speeds. These revelations transform our understanding from a static, mechanical view to a dynamic, interconnected cosmic dance. We're not passive observers, but active participants in a universe where space, time, matter, and energy are intimately woven together in ways that continually challenge our imagination. And here's a fascinating personal connection. Right now, as you listen to this explanation, time is actually flowing slightly differently for different parts of your body. Your head, being slightly further from Earth's center, experiences time marginally faster than your feet. It's a subtle reminder that the mind-bending principles of general relativity aren't confined to distant astronomical phenomena. They're happening right here, right now, in the most mundane moments of our existence. Einstein's profound insight extends far beyond mathematical equations and astronomical observations. At its core, general relativity offers a deeply philosophical understanding of our place in the cosmos, a revelation that fundamentally transforms how we perceive ourselves in relation to the universe. Every single object, from the most massive galaxy to the tiniest grain of sand, is an active participant in the cosmic dance of space-time. We are not passive observers standing outside of reality, but integral components of a dynamic, interconnected cosmic fabric. Each of us contributes to the geometric tapestry of the universe, warping and shaping space-time through our very existence. Consider the remarkable implication. Your body, right now, is creating its own unique curvature in the cosmic landscape. The mass of your physical form generates a subtle but real distortion in the fabric of space-time. When you move, when you breathe, when you interact with the world around you, you're literally reshaping the geometric structure of reality at a microscopic level. This perspective dismantles the traditional notion of separation between observer and observed. We are not simply watching the universe, we are the universe experiencing itself. Our consciousness, our physical presence, our interactions are all part of an intricate, interconnected system where every element influences and is influenced by everything else. The human element in general relativity reveals a profound unity. The same fundamental principles that govern the movement of galaxies apply equally to the most minute interactions happening within your body. The gravitational dance that guides celestial bodies is the very same geometric principle that allows you to sit, stand, or move through space. Einstein's theory invites us to see ourselves as cosmic participants. We carry within us the same fundamental laws that shape stars, black holes, and entire galaxies. Our individual existence is a unique expression of universal geometry, a localized manifestation of the broader cosmic architecture. This perspective offers a humbling yet empowering view of human existence. We are not insignificant, we are integral, not separate from the universe, but a living, breathing embodiment of its most fundamental principles. Every action, every movement, every moment of our lives is a direct interaction with the cosmic fabric of space-time. In essence, general relativity transforms our understanding from a mechanistic view of reality to a holistic, interconnected experience. We are not just inhabitants of the universe, we are an active, dynamic expression of its ongoing creation. General relativity continues to be a cornerstone of our cosmic exploration, proving itself as a remarkably resilient and predictive scientific framework decades after its inception. The theory's ongoing relevance is demonstrated through groundbreaking scientific achievements that continue to validate Einstein's original insights. One of the most spectacular recent confirmations came with the first ever image of a black hole in 2019. The Event Horizon Telescope captured an image of the supermassive black hole at the center of the M87 galaxy, providing visual proof of phenomena predicted by general relativity. This breakthrough allowed scientists to directly observe the extreme warping of space-time around a massive cosmic object, exactly as Einstein's equations had predicted a century earlier. The detection of gravitational waves in 2015 marked another pivotal moment in scientific validation. These ripples in space-time, caused by massive cosmic events like black hole mergers, were another direct confirmation of Einstein's most radical predictions. The Laser Interferometer Gravitational Wave Observatory, LIGO, opened an entirely new way of observing the universe, allowing scientists to listen to cosmic events that were previously invisible. Future space exploration will increasingly rely on general relativity's principles. Missions to understand dark matter, dark energy, and the fundamental structure of the universe will depend on our ability to comprehend space-time's complex geometry. Space agencies are developing more sophisticated technologies that can measure the most minute gravitational effects, pushing the boundaries of our understanding. Emerging technologies are finding innovative applications of the theory. Quantum computing, for instance, must account for relativistic effects to maintain accuracy. Navigation systems, satellite communications, and global positioning technologies continue to require precise relativistic corrections to function effectively. The search for a unified theory of physics remains one of the most exciting frontiers. Scientists are working to reconcile general relativity with quantum mechanics, seeking a comprehensive framework that can explain the universe from its smallest particles to its largest structures. This quest continues to be guided by the fundamental insights Einstein first proposed. Climate science and Earth observation also benefit from relativistic principles. Precise measurements of gravitational fields help scientists understand planetary changes, sea level rise, and complex geological processes. Atomic clocks, which rely on relativistic corrections, provide unprecedented accuracy in measuring time and planetary movements. As we push further into space exploration, general relativity becomes increasingly crucial. Future missions to understand black holes, detect gravitational waves from distant cosmic events, and explore the fundamental nature of space and time will continue to build upon Einstein's revolutionary framework. The theory reminds us that our understanding of the universe is an ongoing journey. Each confirmation, each new observation adds another layer to our comprehension, revealing a cosmos far more complex and interconnected than we ever imagined. The most profound beauty of general relativity lies in its fundamental revelation of cosmic unity. Gravity, which might seem like a force that separates and pulls things apart, is actually the most powerful manifestation of universal connection. Every object in the cosmos, from the smallest particle to the most massive galaxy, is interconnected through the intricate fabric of spacetime. Imagine the universe as a vast, dynamic tapestry where every movement, every interaction creates subtle ripples and curves. We are not isolated entities moving through an empty void, but active participants in a cosmic dance. Each of us follows a unique path through this shared spacetime, our trajectories influenced by and simultaneously influencing the geometric landscape around us. This perspective transforms our understanding of isolation into a profound sense of cosmic belonging. The same fundamental principles that guide planetary orbits, bend starlight, and shape galactic structures are actively working through our own existence. We are not separate from the universe. We are the universe experiencing itself through countless individual perspectives. Every moment of motion, every breath, every step you take is a complex interaction with the cosmic fabric. Your mass creates its own subtle curvature in space-time, connecting you to the broader geometric structure of reality. The boundaries between individual and universal blur, revealing a deeply interconnected cosmic experience. As we conclude our journey through the mind-bending landscape of general relativity, we invite you to continue exploring. The universe is a realm of endless wonder, where each discovery opens doorways to more profound questions. Next week, we'll dive into the equally fascinating world of quantum mechanics, another frontier that challenges our understanding of reality. We're not just observers of the cosmos, we're active explorers, continuously unraveling its mysteries. Join our cosmic community, subscribe to our channel, hit the notification bell, and share your thoughts. Your curiosity drives scientific exploration, connecting us all through our shared quest to understand the extraordinary universe we inhabit. Until next time, keep exploring, keep wondering, and remember, you are an integral part of the cosmic dance.